here's Marilyn's argument, basically. Suppose you play over and over again. In the long run, a third of the time, your first guess is going to be right. Right? Because the long run, a third of the whatever. Say you always pick door A. Third of the time, it'll really be behind door A. And so if you stick with your original guess, you'll win a third of the time. What happens the other 2/3 of the time? Right? The other 2/3 of the time it's behind one of the remaining doors, but the host shows you which one it isn't behind. And so that other 2/3 of the time, if you switch, you'll win. Right? Does that make sense? 2/3 of the time it's behind one of the doors you didn't pick. When that happens, if you switch, you win. 1/3 of the time it's behind the door you did pick. When that happens, if you stick with your original guess, you win. Okay? So divide the universe of possibilities up into two things. It's behind your original guess or it isn't. The chance it's behind your original guess is a third. The chance it isn't is 2/3. If you always stick with your original guess, you win a third of the time, because a third of the time your original guess was right. If you always switch, you win 2/3 of the time, because 2/3 of the time it's behind one of the other two doors, and the host has showed you the one that isn't behind. The only one left is the one that it is behind. That makes sense? Okay. So what's wrong with the math? How can the math be wrong? It calculates the wrong thing, okay? There's no algebraic error, there's a conceptual error. The right story, the right thing to calculate is not the probability that it's behind door C given that it isn't behind door B. That's not an accurate description of what happened. It's what's the probability that it's behind door C given that you picked door A and the host revealed to you that it isn't behind door B, right? The fact that you picked door A, the host knew which door you picked, and then using that information decided which door to show you, which door to open. That essential ingredient is missing. The professors calculated the wrong conditional probability, okay? So let's see if we can now work through the right calculation. So what's the chance that it's behind door C, given that you pick door A and the host reveals that it isn't behind door B? A little more complicated thing to think about. Well, we're going to divide the universe of possibilities. So under what circumstances, okay, if I pick, I need an extra assumption here, which is what happens if I pick a door that doesn't hide the prize? Which door is the host then going to show me? And we're going to pretend that if I pick door A and it really is behind door A, then the host tosses a coin to decide whether to show me door B or door C, right? If I pick door A and the prize really is behind door B, the host doesn't have a choice. He has to open door C. If I pick A and it's really behind C, he has to show me B. He doesn't have a choice. That makes sense? But if I pick door A and it really is behind door A, he has a choice. I'm going to pretend he tosses a coin to make that choice. All right, so we're now going to use the idea that the door that I pick is independent of the door that it's actually behind. I don't have any information to help inform my original choice. So what's the chance that that it actually is behind door C and I pick door A? Well, my pick is independent of how the prize was hidden. So the probability that it is actually behind door C is a third. The probability that I pick door A is a third under the assumption that I'm making. The probability of both of these events, they're independent, so it's the product of their probabilities, that's a ninth. Okay? So far, so good? All right. So now I want to think about what's the probability that I pick A and the host shows me that it isn't behind door B. Well, there's two ways that the host can end up showing me that it isn't behind door B. Right? One way is I pick A, it's actually behind door C. Host doesn't have a choice, has to show me door B. Yes? The other way is I pick A, it really is behind A, host tosses a coin, 50% chance the host then shows me that it isn't behind B, 50% chance he shows me it isn't behind C. So far, so good? All right, so if I pick A, okay, so I'm partitioning the event that I pick A and the host reveals that it isn't behind B into two disjoint events, right? They're disjoint because if it really is behind A, it isn't behind B or C. That's what I'm partitioning on. So chance that it is behind A and I pick A and the host shows me that it isn't behind B, plus the chance that it really is behind C and I pick A and the host shows me that it isn't behind B. So what's the chance of this? If it's behind A, what's the chance? So the chance that it's behind A and I pick A, we already figured out as a ninth, right? Okay. If it's behind A and I pick A, half the time the host is going to show me that it isn't behind B, half the time the host is going to show me that it isn't behind C. Right? So this probability is half of a ninth. Okay. What about this? If it's actually behind C and I pick A, chance of that is a ninth, right? But the host then doesn't have a choice. If these two things happen, the host has to show me that it isn't behind B. Has no choice. So the probability of this piece is a ninth. So I have an 18th plus a ninth. Does that make sense? All right. Okay, so now I have all the pieces that I need to do this calculation. What's the chance that it really is behind door C, given that I pick A and the host reveals that it isn't behind B? Well, that's the chance that it is behind C and I pick A and the host reveals that it isn't behind B, divided by the chance that I pick A and the host reveals that it isn't behind B. The chance of this is this thing we just figured out. That's an 18th. I'm sorry. Yeah, that's a ninth. And this other piece is a ninth and an 18th. So we have a ninth divided by a ninth plus an 18th. It's 2/3. Sorry? I'm finding a conditional probability. So the conditional probability of C given this and this is the probability of C and this divided by the probability of this. Okay. So this agrees with Maryland's solution. It says that switching is the better strategy. If I switch, the chance I win is 2/3. If I stick with my original guess, the chance I win is 1/3. So the problem is not in the arithmetic. The problem is in what is the conditional probability you were trying to compute. The problem is in the conception.